Yeah, this will just be me basically working out some problems from chapter 1 of Spivak's calculus book. So chapter 1 is a little basic, so if I keep doing this regularly and get to the later chapters, I'll probably go through some of the content before I work on the problems. But this one it's mostly just just the field axioms and the order axioms, and then there's a proof of the triangle inequality. Yeah, it's pretty straightforward, nothing too special. Although there's this interesting second proof which he shows, which I maybe will write out in its entirety, because it's actually this idea shows up in different contexts, like linear algebra. One sec. So the triangle inequality, it just says this for all real numbers a and b. Now, I guess at this stage in the book, he's just calling these objects numbers because the full characterization of real numbers isn't really within reach yet. So you need not only the field axioms, but the least upper bound property. In the next chapter, he goes through a proof of the irrationality of square root of 2, which kind of points to the need for another property in order to deal with real numbers. But I'm just gonna write this. Okay, so yeah, and this is like official proof of this fact. He splits it up into cases, which is kind of the go-to technique when you're dealing with absolute values. But another thing you can do is actually use squaring to get rid of the absolute value sign. This is actually really useful in like higher dimensional problems too, because there's this object called a norm, which is actually very analogous to absolute value. Well, absolute value is a special case, but for vectors, if a vector has a bunch of components, say it's an n-dimensional space, then the norm is defined to be the square root of the sum of the squares of the components. This looks kind of weird, but it's actually just a direct generalization of the Pythagorean theorem. In fact, if you write down this definition for x in R, and put the double bars just to emphasize that we're writing the expression for the norm, this would just be the square root of x squared, the only component. But this is actually exactly equal to the absolute value. And right, so the triangle inequality, it's actually one of the defining properties for this type of thing. It's called a norm. I don't really know where I'm going with this. I'm just saying stuff, but yeah, it's It's just analogous. Okay. Anyway, so to prove this inequality here, what we do is work out the absolute value of a plus b all squared. Since the absolute value is a positive number, and squaring actually will turn a negative into a positive, you are allowed to drop the absolute value bars when you're squaring on the outside, and that can be convenient because you no longer have to split things into cases. The disadvantage is if you want to undo the square root, then it's kind of ambiguous. Taking a square typically destroys information, so yeah, you can't just like take the square root and then be done with absolute values. They'll come back. So anyway, we now can expand this just using the usual method, or whatever your favorite way to look at that is. Right, so now we have an a squared, a b squared, each of which are positive because we're squaring real numbers. 2ab, we don't really know. However, what we can do is actually bound this above by the following expression. Okay, so what's the point of doing that? Well, if we look what we're trying to get to, if we want to end up with this on the right hand side, I mean, we really want to end up with that to the power of 2, because at the end we're gonna remove that power of 2 by taking square roots. Right, and so by doing this, we replace the a and the b with their absolute values respectively. This, if either of those happen to be negative, then it will give you something that's at least as large by replacing it with the absolute values. Okay, so what you can also do is put absolute values in here without changing the expression. That's perfectly valid, but now you'll notice that this is exactly the expansion absolute value a plus absolute value b all squared. Right. And we also know that whatever this was, it's non-negative because it's an absolute value that's been squared, so it's guaranteed to not be negative. And it's a fact that if 0 is less than x squared less than y squared less than or equal to y squared, then 0 must be less than or equal to x less than or equal to y. So in other words, the square root function preserves the order of real numbers, and at least if they're positive or non-negative. So so we can drop that square here since we are working with positive values. And we just get this. Okay. Now I want to go start on these problems. So yeah, I'll just look at number 1. This is actually in 6 parts, so I'll only do a couple. So it's just asking to prove these equations, which look very simple, but You have to remember that we are actually, we're only allowed to assume these really basic fundamental field axioms. So even these simple looking things require a little bit of care. Yeah, the fact that I mentioned about the square roots, we'll get to that eventually. This will be treated later. It's one of the problems. Yeah, okay, so what this one says is that if ax equals a, and a is not equal to 0, then x must be 1. So remember, every field has a multiplicative identity. That's what the 1 stands for. This doesn't necessarily have to be like real numbers or even rationals. It could be some other number system. Actually, at the end, you can actually define a field which has only 2 elements, a 0 and a 1. And so anything that we prove using only the field axioms must hold for even that special case, or any field for that matter. The way we want to do this is we want to look at the quantity ax minus a. Okay, I don't remember. Well, usually when you do these really pedantic proofs, you like write down the property you're using on the side, but I don't remember the numbers of what properties are which. So I'll just tell you which one I'm using, and yeah. Okay, so the idea here is we want to show that this ax minus a must equal 0. Or, oh, sorry, we know this equals 0, right? Geez. Yeah, and our goal is to show that x is equal to 1. Actually, you know what? I think it would be easier to just do this directly. So if ax equals a, since a is non-zero, we know that we can multiply by the multiplicative inverse, which exists as long as a number is not zero. Okay, and we also know that multiplicative inverse times a number gives you 1. That's the definition of it. Okay, so we have a inverse times ax equals 1. Now we use the property called associativity. Basically says that multiplication is invariant under vocal inflection. So a inverse times ax is the same as a inverse times a times x. And that must be 1. Well, we just saw also that a inverse a equals 1, so we know that 1 times x equals 1. And now the defining property of the 1 is that it's the multiplicative identities, which means multiplying it to anything leaves the value unchanged. And so the left-hand side is just going to be x. Okay, and that's the end of the proof. Usually people put this little square box or a QED sometimes at the end of the proof. Some of them don't put anything at all, which can be kind of frustrating because if you're trying to skim through a book, you don't know like where the argument ends and the next part of the book begins, but I digress. Okay, I'll do the next couple probably. So we now want to show x squared minus y squared is equal to x minus y, x plus y. This is the classic difference of squares formula. But since we're trying to do it with minimal assumptions, we can't really just use FOIL or however you want to think of it. because that's not really one of our axioms. We're basically trying to prove that the FOIL method works, essentially. So it's actually easier to start with the right-hand side. This is a case where in making a proof, it's easier if you know the answer. So you have to have a way of having guessed this, but then to actually prove it rigorously, it's a bit of a different process. It's kind of something extra. So another example of something like that is mathematical induction, which, yeah, this is notorious because it's totally like you're out to lunch unless you have a guess for what the solution should be. But if you have an educated guess for it, some conjecture, and it works, then it can be really powerful. Okay. So we know by the distributive law that you can multiply any number into a binomial. So maybe we'll call this thing z as a shorthand. So we know we can do this. And we can also switch the order of each of these multiplications by commutativity. And then we can apply the distributive law to each of these binomials separately. By the way, when we write x minus y, what we really mean is x plus the additive inverse of y. So we get x times x plus x times minus y plus y times x plus y times minus y. Right. Now, we would like to show both that x times minus y plus y times x equals 0, which, I mean, and also y times minus y equals negative y squared. Okay, so the way that we would show this for the second one, for example, both these look totally obvious, but we'll just quickly prove them. So the way we would show that this thing is the additive inverse of y squared is you need to show that y squared when added to it gives you 0. So we want to end up with 0 on the right hand side eventually. Remember, so y squared is just y times y. And then we can factor out a y by doing distributive property in reverse. And y plus negative y, by definition of additive inverse, must be 0. And this is something which can be proved, which is that anything times 0 is 0. It's not an axiom, but it's a pretty basic thing to prove. Alright, so that's what we needed. That shows this. For this other one, so this one's also not too bad. We want to first switch these two around. So that'll be x times minus y plus y. And again, minus y plus y is 0, so x times 0 gives you 0. And there you're good. So we can cross these off, which is, I mean, obvious, but again, we're following the axioms to a fault. So we have x squared plus the additive inverse of y squared, which can be written as in shorthand as x squared minus y squared. Okay, so we're done. Let's skip ahead a little bit. All right, let's see. I'm going to skip problem 2. Let's do number 3. First part. So A over B is equal to AC over BC. If B and C are non-zero. Right, so this, I mean, it's just an obvious cancellation property of fractions, but once again, we want to do this totally rigorously. So first of all, A over B, you can write this in the more for primitive terms in this way. Where we take number times the inverse of the denominator. And this is what we're trying to show. Okay. So one important property that we need is that A times B inverse equals B inverse times A inverse. So remember if we call this like this thing, I don't know, like Q or something, doesn't matter. So the property of AB inverse, like if we're proposing B inverse A inverse as a candidate for the value of the inverse of A times B. By the way, if A, B are non-zero. This is a separate line of reasonings, by the way. Okay. So if A and B are non-zero, right, we want to show A times B inverse equals B inverse A inverse. In order for that to be the case, we need this to hold. A times B times Q is equal to 1. And that's pretty obvious because, well, you can see if you just rearrange the brackets, everything sort of cancels out from the inside, moving outward. Question mark here. So we really have A times B inverse times A inverse. And now this inside will collapse and turn into 1. A times 1 times A inverse, which is just A times A inverse. And then that turns into 1 again. So, right, it all collapses from the inside out. This formula here, so you might be wondering why I switched the order of A and B. For like real numbers, it doesn't actually matter, but there's certain contexts, like when you work with matrices, where you can't actually flip the order of things all the time. And it's important to write the inverse in this way so that you get the proper cancellation, because otherwise it's not necessarily going to be an inverse. Okay, so with that in mind, this right-hand side can be written as A times C times C inverse B inverse. And you can see that the C and C inverse will cancel out, just like our proof over here. We just are left with a times b inverse at the end, which is the left-hand side, obviously. So, yep, that holds up. I just checked that problem 3, or the third part of this problem, actually asks to prove this thing I did on the right hand side over here, so I probably wasn't supposed to use that to do this part 1. Oh well, I think it's fine. I'm actually not sure how he was expecting that to be done. Well, okay, I'm going to move on to part 5. So this is a over b divided by c over d. This is the multiplication by the reciprocal property. We divide two fractions, and of course we need to make sure that anything which makes a denominator go to anything appearing in a denominator can't be 0. Okay, so let's kind of remove the fractions from all this. So what this is saying is that A times B inverse, C times D inverse, but all of that's an inverse, equals AD times BC inverse. Okay, so I think we're going to work with the left-hand side just because the right looks more complicated. Well, maybe we'll look at both, but let's just look at this term in particular first. So C and D are non-zero. Now, if a number is not 0, its inverse must also not be 0, and that's just because if an inverse were 0, if it equals 0, then A times A inverse would be 0. But we also know that A times A inverse equals 1, and in the axioms for the field, this isn't allowed to happen. 1 is not allowed to be 0. That's just something that's postulated. C and D inverse are both non-zero, which means we can use our inverse formula to split this up. So this turns into D inverse inverse times C inverse. Right, and now we also can show that D inverse inverse equals D. The inverse of an inverse is always the original number itself. And the way you do this is just by using like the property of the inverse. So it looks a little confusing, but to be the inverse of D inverse, you have to be something which when multiplied to D inverse gives you 1. It's just by symmetry of the inverse property. So the fact that D times D inverse equals D inverse times D gives you 1. This implies that D is the inverse of D inverse. Okay. So that's just equal to D. That's a C inverse. A times B inverse. And then of course on the right hand side we just get A times D times C inverse times B inverse. And you can commute and commute all these things. We have the same things appearing on both sides, so they must be equal. All right. Let's see. I'm trying to find an interesting problem. All right, let's look at some of these inequality ones. So A less than B, and C is less than D, and then A plus C is less than B plus D. So the things we're allowed to assume are the order axioms, which off the top of my head I don't remember, but I have a feeling. Well, anyway. So if you start with a thing you know to be true, order relation of this sort, you can add the same thing to both sides. So since we're trying to look at A plus C on the left, we certainly know this is true. So we know how to compare A plus C to B plus C. Now that's okay, but we ultimately want B plus D on the other side. That's not a problem. We can use C less than D. So the fact that C is less than D implies now we want to actually add B to both of these. Okay. And now you can see what we have. A plus C less than B plus C, which is less than B plus D. And so this inequality is proven since the relation is what's called transitive. If you have one thing less than a second thing and the second thing less than a third thing, then the first thing was less than the third thing. All right, let's move on to a different one because these are kind of simple. So 7. Prove that if 0 is less than A less than B, then we must have A less than square root of AB less than A plus B over 2 less than B. Okay. Now, we can do this in stages. So 0 less than A less than B. Since A is positive, we can actually multiply the whole thing through by A, which gives us 0 less than A squared less than AB. And now we can take square roots across this inequality. That was dealt with in one of the parts of problem 5, which I've skipped, just because there's so many of them and it kind of just take a long time. But we can assume that. So this now implies 0 is less than a, less than the square root of ab. We don't have to do plus or minus on this square root because we're just taking the positive solution. Okay, so that proves this piece of the inequality. The second part is actually pretty easy if you work backwards. So this here, we can multiply both sides by 2, which gives us this. And now you can subtract b. So subtract b from both sides. It gives you the original inequality, which we know to be true, which says that a is less than b. Obviously, you can reverse all these steps. You have to be a little careful when trying to like reverse square roots in general, but here there's no issues of that sort. Okay, so that one's good. That one's fine. This one's fine. We just need to worry about the middle one now. Alright, so 0 is less than square root of ab, less than a plus b over 2 is what we are trying to prove. So yeah, we can again work this out by working backwards. Multiply the whole thing by 2. We get a 2 square root of ab less than a plus b. And these are all positive still. So now we can actually square everything because everything's positive, so it'll preserve the ordering. Just square this, and I'm going to expand this binomial out. And now if we just look at this piece and subtract the 4ab over to the right hand part, and then we can factor this thing again. It's just a perfect square, only this time it's a minus b all squared. Now there's a potential issue because, well, we know a and b are both positive, but we need to also be sure that they're not equal, and this is actually part of the assumption. So we know that a is less than b, so this last thing we've written down is in fact true. The square of a minus b is going to be strictly positive because a and b cannot be equal. That's the only way it could be 0, and it's always not going to be non-negative. So you can also check that you can reverse all these steps. So if we started with this, when you write the proof out, you kind of do it in the reverse. So we would start with this 0 less than a minus b all squared. We can expand that out and then just kind of by inspiration add 4ab to both sides. And then by assumption, 4ab is bigger than 0, so then we get the whole the triple inequality. And then we can take square roots since everything's positive. Alright, so that finishes that. Okay, I'm gonna go now to problem 9. So this is just a bunch of examples involving absolute values. Trying to simplify. Yeah, so what it asks is to write the expressions with at least one less pair of absolute value signs, which is kind of vague, but yeah, whatever. Alright, so this first one's easy because 7 is bigger than 5, which is bigger than 0, and that implies the square root of 7 is bigger than the square root of 5, which is bigger than 0. So, in particular, this thing is bigger than 0. And obviously this thing is bigger than 0. It's the sum of two positive numbers. So we can just drop the absolute value signs. It's no big deal. Okay, second problem. This one. Whoops. A plus b minus absolute value minus absolute value b. Right. So this looks an awful lot like the triangle inequality, which I wrote up at the top. And it's just this what you would get if you moved everything over to the left-hand side. But what the triangle inequality tells you is that that whole thing is less than or equal to 0. So we put absolute value bars around it. That's actually just going to flip the sign around. So this is going to be the same thing, but with a negative out front. Because the result needs to be positive, or at least non-negative. Okay. I'll skip to problem 10 now. So this says express each of the following without absolute value signs, handling each case separately when necessary. Okay. So for this one, let's first split into the cases for B. So there's two possibilities. B is either going to be non-negative or it'll be less than 0. If B is non-negative, I'm going to leave the other one in absolute value intact for now. But we can drop the one on B if B is bigger than or equal to 0. This minus sign is just going to stay in front. If B is less than 0, then we're going to have absolute value A plus B minus negative B. Or, in other words, A plus B plus B. And now, in each of these things, we need to examine the following cases. So A plus B could be non-negative, or it could be negative. And then in the first case, it's A plus B minus B, and then in the second case, it's the negative of A plus B minus B. And you have the same two cases for this situation. Again, A plus B plus B, A plus B to negative plus B. So this gives you A, and then this gives you this negative A minus 2B. It's all pretty straightforward. Right. So we get these 4 possibilities depending on the values of A and B. Let's see. Kind of interested to plot their regions in the A-B plane, where each of these things occur. So the B bigger than or equal to 0, that's kind of the upper half plane here. So this first case, B bigger than or equal to minus A. So the line B equals minus A is here. So this is the kind of crucial piece. And to be bigger than that, that's just all the stuff over here. But remember, B is also assumed to be positive, so we actually don't go below the horizontal axis. I'll call this region 1. So in region 1, the one I've colored in blue, that's where the expression is equal to A. Alright, so in region 2, A plus B is less than 0. It's B less than minus A, but B is also assumed to be in the upper half plane, so that's just all this stuff. It's the other part of the upper half plane. And so in this region, we get expression 2. And you can similarly color in the other ones. So in the bottom, there's 3. And finally, I guess I'll use this gray pen. This is 4. All right, so that's kind of interesting. Yeah, let's move on to the next one. Right, I just want to Oh, I just looked at the chat. Yeah, sorry, I did not look at that yet. Oh, I can do a pop-out chat. Oh, interesting. Oh, so I can just, yeah, I can just like put it in the corner. Cool. I'll just like squeeze it a little bit. Oh, it doesn't actually go more. Oh no, there it is. All right, so yeah, let's do the next one of this. These ones are a little more interesting. Oh, well, there goes the pop-out chat. Guess I could squeeze the window over to the side a bit. That works. Bring this down. Yeah, that seems fine. All right. Okay, so the two. The absolute value of x minus 1. All right. So we can again split this one up into several cases. The thing here that makes this one kind of weird is that we've got absolute value inside an absolute value. The most natural thing to do is probably to look at the inside one first. So depending on whether it's bigger than or equal to 0 or less than 0, we'll deal with the outer one later. So here, if it's positive, then we get that's just equal to x. I mean x minus 1, but the x absolute value of x is just x. And then if it's the negative, you get negative x minus 1. So yeah, now actually this negative x minus 1 simplifies to just x plus 1 because you can just pull out the negative sign and the absolute value will kill it. Okay, so then we get two more cases, or two more pairs of cases. X bigger than or equal to 1 and x less than 1. And then here, same thing, but for negative 1. That's kind of the switching point. Oh shoot, jeez. X plus 1 and the negative of x plus 1. Right. Alright, so this is a problem involving just one variable, so we can actually plot these crossing points on a real line. So the first thing is determine when x was 0, and then the other important points are 1 and negative 1. So you can actually see the four regions really clearly. It's just the stuff between these 3 points and also going off to infinity and negative infinity. Yeah, and you could plot this function as just a piecewise linear thing. So it'll be continuous, but we'll have cusps at these points. just trying to find another good one to do. Let's try this one. So 15. If x and y are not both 0, then x squared plus xy plus y squared is bigger than 0. Or, in other words, we're trying to prove x squared plus y squared is bigger than negative xy. Zeros with lines through them. I don't know if I can. I don't know if I can do that. Maybe. Okay, just this once. I can't forgive myself though. Okay, so if x equals 0 or y equals 0, the statement becomes trivial. So by symmetry, we only have to look at one of these cases. So if x equals 0, we're supposed to be consistent, then we just have y squared bigger than 0. Which must be true because if x were 0, y must not be 0. They can't both be 0. And the same thing for if we assume y is 0. So this must hold. So we might as well assume x is not 0 and y is not 0. Okay. All right, let's see. So now, like if they're both positive, then it actually becomes obvious because this is bigger than 0, which will then be bigger than negative x times y. And that's the same if they're both negative. So we might as well assume that they have opposite sign. And we might as well just make x to be the positive one because this is symmetric. So okay. And so we want to compare this with x times negative y. Okay, let's That amounts to just proving this. Oh, alright. Yeah, I think I've got it now. So, since y was negative, that means minus y is positive, so it equals the absolute value of y. And so now we've just reduced it to showing this. Or proving this if x and y are both positive. Maybe this hopefully is not too confusing. But if we can prove this last statement that I've written down, then we can just kind of work our way back up. And yeah, we will have proved the thing we started with. The reason this is true is because this quantity is bigger than or equal to 0, which means that we can do this. Right, and the fact that x and y are both positive means that we can make this strictly bigger than x times y. And so we get what we wanted. This, oh, the cap. Yeah, I haven't looked into that slang yet. I still need to Google that. Yeah, so that was a little disorganized, but hopefully the message got across. You might want to clean that up a little bit, but all the important stuff is there. I don't know, should I write the proofs out super neatly, or I don't know. I just feel that would be kind of boring. All right. So for 17, so this one asks to find the smallest value of 2x squared minus 3x plus 4 oh, there's a lag. Is it possible to change that? Wait. Yeah, I don't think I can edit it once it's running. Alright, so the strategy for this is to complete the square. Right, and this is a procedure that is drilled a lot in high school, but a lot of people forget it. I sometimes feel like I've forgotten it. But you first start by grouping these two things together. So we want to factor out the 2 here. And now we just want to ask, if I look at this quadratic, what constant term would it need to have in order to become a perfect square? And then we're going to add and subtract that term. It's a really common trick in math, where when you want something to be there, you just sort of put it in, but you always have to compensate by subtracting it. You can't just change things without consequences. To deal with the consequences of our actions. So x squared, dropping real profound truth. Yeah, let's. Okay. Oh gosh, I'm totally drawing a blank. This should be. Maybe you can guess what it should be before I can. I think 9/16. Oh yeah, what did I just say? We can't just put that in. We have to subtract it. Right, so now we want to multiply the 2 not into everything, but just into this triple, and then this thing we subtracted off. So basically we want to keep these 3 guys together. They're best friends. Yeah, this turned out right. So now it's x minus 3/4 squared, and the reason we picked a 9/16 is because when you expand this thing out, 3/4 is what you need in order to get that constant on the x term. Alright, and then we just have this this stuff, which is left over. So 9/8 plus 4, and then that's 32 minus 9, which is that 23/8. Gosh, I think so. My brain is not doing well with mental math right now. Plus, because the 4 is very positive. Okay, what was the original question? It said find the smallest value. Right, completing the square was just the way we're trying to figure this out. So when you learn the like all the techniques of calculus, you'll find much more robust ways of solving this sort of problem, finding minima or maxima of a function. But for quadratics, you can just use these high school techniques and they work fine. So the idea here is that the thing that's being squared is always going to be non-negative. And so it actually equals 0 for exactly one value of x. This thing equals 0 if and only if x equals 3/4. And when x is equal to 3/4, our expression, I'll call this whole thing q for quadratic, q of x. So q of 3/4, that's going to be 23/8, just the constant term. Yeah. And that's the smallest value, because for any other value of x, it's a little bit larger. All right. So now b is kind of interesting. It's the same for x squared minus 3x plus It's 2y squared plus 4y plus 2. So here we're going to complete the square 2 times. I'll try to do this quickly. Let's see, y plus 1 squared minus 2, I believe. Yeah, I think that's right. Anyway, these 2's will cancel, and then we get this thing. So here's an expression with 2 quadratic terms, each of which is non-negative, of course, and then we have our minus 9 over 4. So it's once again the constant term. That's the minimum for any value of x and y that isn't x equals 3/2 and y equals -1. You get something a little larger. Okay, so there's quadratic formula. Yeah, just trying to roll into a couple more. Alright, so these last few problems, okay. Well, there's one on the Schwartz inequality, but I'm going to skip ahead to these ones with involving epsilon. Okay, so we're going to suppose x minus x naught is less than epsilon over 2, as well as y minus y naught less than epsilon over 2 in absolute value. So we have to show, given that information, that x plus y and x naught plus y naught will differ by at most epsilon in absolute value. Okay, and similarly the difference as well. So with the same choices for the epsilon over 2 above, the errors in the difference will again be controlled by epsilon. The error in the difference, sorry, is just one. Alright. So this, we'll just look at the one with the sum. So we're going to try and re-express this sum in terms of these things here. So we understand these two things, and we want to control the absolute value, the difference of the sums. So what you want is actually to bound it above by something which you know to be small. Before I do that, I could leave it as less than or equal, I suppose, but I just want to rearrange the stuff inside. Oh, is that a Rundi? Okay. Oh my god. Yeah, I could just start reading directly from the textbook with no expression. Oh my gosh. Alright, so now the trick is just to use the triangle inequality. It's just a matter of rearranging stuff. This is strictly less than epsilon over 2 plus epsilon over 2. So we've written it in terms of the stuff we can control. So the difference is totally similar. I mean the y things have just changed sign, but when you do the triangle inequality, that just amounts to switching the order that they occur in the absolute value, so it really doesn't change anything. Alright, so for 21, it's the same problem, but for the product, I'm not going to write down the expression that they give for epsilon. We'll try to figure it out ourselves. The trick with this is to add and subtract the same thing twice, and it's kind of a little tricky to see what you have to do. But you want to introduce this thing which has one piece in common with both the left and right hand sides. Oh, by the way, we know x minus x naught and y minus y naught are less than something small. Okay, I know that's not a very rigorous way of writing that, but whatever. Okay, so we can then factor out a common factor from each of these pairs of terms once we group them together in this way. Okay, and now we want to apply the triangle inequality. So I'm going to split this up like this. Okay. So we want to try and make both of these things less than epsilon over 2. That's the idea. If we can do that, then the sum will be less than epsilon. Alright, so this one on the right, can deal with that first. So saying that's less than epsilon over 2, that'll be guaranteed. If this is less than epsilon over 2 absolute value, why not? Now, there's one extra thing you have to be careful. We don't know that the y0 is non-zero. But that's not a problem. We can actually just make this smaller. So, sorry. What am I? Yeah. If you increase the denominator, it gets smaller. Geez. Yeah, so if we make bound x minus x naught above by something smaller than what's strictly necessary, then that quantity which we want to be less than epsilon over 2 will still be less than epsilon over 2. Okay, so this is the small thing that we want to choose to control x minus x naught. Now you might think for y minus y naught it's going to be the same thing, but that's actually not the case, because this x is a variable, so we don't know what x is doing. Like this is supposed to just be a fixed thing that we pick at the very beginning, because we're trying to say, like, if x is close enough to x0 and y is close enough to y0 from the start, no matter what those values are, if they're just this close, you can vary them any way you like as long as they remain that close. But if our error for y actually depends on x, then the error will be changing as we vary x, so that's no good. So what we need is to figure out how do we make x as large as possible. Well, we can actually we can go here and figure out what the largest value of x will be. So we know x minus x0 is going to be less than this quantity here. And I mean, you've also got the thing with the negative, but I'm just going to ignore that. So we'll just disregard this. Not that it's wrong, it's just not important. So x is less than x0 plus all this stuff. Right. Wait. No, I think I messed something up. Oh, is that bad or? Right, so when we do this, we can try to make absolute value of x minus x0. So we can actually force it to be at most 1. I kind of tripped myself up here. But just to make our lives easier, so if it's less than or equal to the minimum of 1 and whatever this mess is, then that implies that x minus x0 itself must be less than or equal to 1. And now using the reverse triangle inequality, you can see that we get absolute value of x is less than or equal to 1 plus absolute value of x0. And so we get this. And that will be less than epsilon over 2 if this is true. Okay. And of course the 1 here is completely arbitrary. You could have just picked like any constant you like. It really doesn't matter. But it just makes everything look a little nicer in the end. So if you pick these just absolutely atrocious values of the error for y minus y naught and x minus x naught, then the error for the products becomes epsilon. Okay. Yeah, so you can also do a similar thing if y and y naught or y minus y naught is small, then you can show 1 over y and 1 over y naught is less than epsilon. Or maybe I'll leave it for you if y minus y 0 is small enough. What small enough means you have to work out it's in terms of epsilon, and 1 over y minus 1 over y 0 will be less than epsilon. Yeah, and then you can also, do the same thing. Oops, shouldn't be crossing that out. So if these things are small, or sorry, yeah, if those two things are small, then x over y minus x over x naught over y naught is going to be less than epsilon. Oh, by the way, like for this one where you're dividing by 1 over y, you also need to assume y naught is non-zero, because you can't divide by it if it's 0. All right. That's basically the end. I mean, there's another problem on the general associativity principle, but probably do that next time, or maybe not at all. I don't know. It's kind of not super important. Yeah. I think I'm going to call it a night. But thanks for tuning into my first stream if you were here. It was fun. I will try to do this more regularly. Next time we'll go through chapter 2 of Spivak's calculus book. Jeez. Things start to get a little more interesting. That's where we have mathematical induction, and yeah, there's a lot of cool stuff in there. That's actually the first. Oh, good night. Yeah, the first part of this book's only 2 chapters, and then we get to functions. So, all right.